So hello everyone, and thank you for attending this talk. I know that the title may seem a little buzzwordy, but I hope that I will present more down-to-the-ground view. So first, few words about me. I am a backend engineer in the machine learning team. So besides of the problems with the regular engineer in the distributed environment, I also have to face and solve the problems of machine learning in cooperation with our data science. Well, if you want to talk with me, I will be really happy to discuss the machine learning, engineering stuff, Python, but also my hobbies like 3D printing and homebrewing. So, what even is NLP? As a natural language processing, we may think of first processing of human voice and voice recognition, but I will not touch the stuff here today. But I will focus on the processing on the already text that we have, textual data. And why natural language processing is hard? First, language is ambiguous. If we say that, hey, I had a sandwich with bacon, it's hard to say whether we met Kevin Bacon for lunch or we had a sandwich with pork meat. Second, texts are compositional. Characters compose words, and then words composes sentences, and finally paragraphs and whole books. And here the problem is that even if we had the same letters that compose two words, let's say burger and pizza, they share none of the characters, but they still carry the meaning of junk food. But we cannot conclude them only based on the characters. So that's a few reasons why this is hard. And if you want to learn more about the traditional NLP approaches and more overview of the NLP itself, I highly recommend you to listening to the last year lecture about Introduction to Sentiment Analysis with Spacey. The slides will be shared with you later, so I will have a lot of links to the further reading. Then, what do common problems we have in NLP? Because, well, if somebody already solved the issue we are having and we can generalize to that, we can either use the ready solution or at least be inspired by it. So the common problems are, for example, document classification, and this also includes document sentiment, whether, for example, the reviews on our business on the website are positive or negative, because if we have thousands or millions of them, it will be hard to classify them by hand. But also author attribution, who wrote the document, and this is a little exciting because not only by the words used, but also by the way they construct the sentences, and also like very practical use case, whether the email we just received is a spam or not, or whether it's important or not. Another common issue is sequence to sequence, and this includes, but it's not limited to, translation, like Google Translate, summarization of text, like we have a whole article and we just want to create abstract of it just to know if we would be interested in it, and also response generation. Really neat feature in Gmail. When we receive an email, we just have one of few possible responses just to tap and respond to our sender. Another common problem is information extraction. We have a sentence, Jimmy bought Apple shares, and Jimmy bought an apple, and we want to know the apple refers to the company or to a fruit. And this is really useful in search engines, or I would say in ads, because when we have an ad, we would want to know it would be relevant, should it be relevant to the fruits, or should it be relevant to iPhones? So these are only a few, the most common ones I would say, but also you will learn, if you want, that there are a lot of them. Why neural networks are good for NLP? Texts carry a lot of features, and we can extract them by hand, we can label them by hand, we can, in sentiment analysis, for example, find and handpick the words that conclude that the sentiment is either positive or negative. Whether if somebody mentions terrible, probably they mean that our business is bad. And the idea is that the neural networks will learn those features on their own. And as the practice shows, they usually do. I will focus and show examples from this quote-unquote real-life problem, the IMDb sentiment analysis. Why I put real in quotes? Because in real life, we do not have such beautiful data sets. These are 25,000 highly polar movie reviews. And first, our real life data will usually not be so polar and not so pure. We will have usually a lot of noise there. So we will have to live with that. But as a exercise, I think it's really good. I will focus as the metrics on the accuracy later, and also as the cost, I will work on the training time. Why training time, not like the number of parameters? Because right now, when we are paying for servers on working on our computer, that's the thing that we are concerned most about. And when we have complex networks, it won't translate directly into that. But the downside is that in the future, when we have better ways of parallelization or better algorithms, we may find out that the networks that are really expensive to run right now will be cheaper in the future. So, like with everything, it depends. What do you choose? Our task definition, we have a movie review. We want to put that in our neural network, and we want to decide whether it was good or bad. So, looks simple enough. But there's a catch on the review itself, because since the neural networks are basically matrix multiplications and additions and also activation functions, we cannot throw text directly there. We need to have some numerical representation. And to obtain that numerical representation, we first need to have some features. So this is an example of the text. Like we can see a big disappointment, incredibly bad, very pretentious. It's highly polar, like I mentioned. But first, to use this text as an input, we need to do something with it. We need to translate first into features, then into this vector. I will focus on the simple sentence, what possible we can extract. A quick brown fox. It looks like we only have a few words, but let's see what we can do with it. First, we can tokenize that sentence. And by tokenize, I mean split into chunks. For the English, most often they will be words. So we have tokens like app, then quick, then brown, then fox. And let's focus for the last one. But if you work with another languages, you may find that it's not so easy, and especially for German, because they glue words together. I do not know German, but I know that there's a case. But you can use a library like SentencePiece from Google to try and live with that, or try some other magic. So let's get back to the word fox. What do we know? Oi. I only touched the cable. Okay, let's focus about the word fox. What do we know about it? If we use classical NLP models, statistical ones, we can extract the information that it is a noun. Or we can label them that by hand, but we can automate it. Also, if we use the WordNet database, we can extract that the word fox belongs to synset. Synset is the wider meaning of the canine. Canine is like doggish animal, let's say, to simplify. Probably if there's a biologist, they will be angry about that. But okay, what else can we know about this word? We can extract its stem. Stem is the core of the word. And we can extract its lemma. Lemma is a basic form of the word. And for that simple case, they will both be fox. If we have an access to the whole corpus of the data, we can also calculate the term frequency inverse document frequency. It tells us basically how important this word is in this given sentence, just to simplify. And it can be another feature. So now, for this specific token, we can have 1, 2, 3, 4, 5, 6 possible features. I will focus on the word itself now, but remember that they are here and they can prove useful. You can also create syntax parse trees from the classical NLP models, and they can also boost your accuracy. When we want to represent a word or a bunch of words in the way that our neural network will understand, we can use, for example, the bag of words. It's the simplest possible representation that I know. First, we construct a dictionary. Here it is constructed from the sentence, a quick brown fox jumps over a lazy dog. And for each word that occurs in our sentence, we assign 1. And for each word we do not have in our sentence, we put 0. And we also usually reserve 1 of the tokens for the unknown words. And now, since we already have a representation, we can work with some network. First, the most basic architecture is fully connected neural network. We have multiple inputs, then we have hidden layer or not, and then we pass our values through it. The important part here is that everything is connected with everything. So we will have a lot of operations. And this is example network. It's constructed by Keras. We have only 1 input, 1 hidden layer, and 1 output. So this is very easy. And after we train that network, what will happen with the first layer? Because it is as big as our dictionary. Here it was 1,000 words on this IMDb data set. And each row will contain now really dense representation of a given word, as it is very often called embedding. So our first layer will construct embeddings for this for words in our dictionary. And what we can do with that, we can use it as a features in different models, but we also can visualize it. I reduced dimensionality from 64 to 2 by t-SNE, and we have this beautiful scatter plot. But what information can we extract about it? As it was also stated in the first keynote, we can look at the similarity. Here I looked at the similarity to the word ridiculous, and the closest words to it are waste, boring, worst, worse. So our network, without even knowing the meaning of the words, learned that they basically mean that the review was bad. On the other hand, if we choose the word fantastic, the nearest neighbors are excellent, 7, probably like on the numeric scale from 0 to 10, simple, 8, amazing, and so on. And if we compare where these two, I would say, clusters are, they will occur in totally opposite points in space. On the one side, we will have the representation for the positive sentiment, and on the other hand, for the negative. So this is nice tools always to show to your company, hey, because it looks awesome. If you use the tensor board for visualization, you can do the t-SNE already there. You do not have to do it by hand earlier. And you can move around this interactive, also 3D graph. Pros and cons of fully connected network with a bag of words as a representation. It's simple, so it's cheap and fast to train. One epoch took about a second or 2 in Colab, so it's you can iterate on it fast, and that's also a really good upside, because then you can conduct experiments really, really quickly. We always look at the whole text, because at every word. It's kind of interpretable, because it's so simple that we usually can explain why the given result was chosen. But the downside is that we can get close state of the art. My best result was about 89%. Current best result is 96%. And we also do not carry the order of the words, because it's just a bug, just a set. We'll lose that information. So how can we fix the thing about the order of words? Let's consider this 2 reviews. I loved the movie, but cinema was terrible. I loved the cinema, but the movie was terrible. If we put them together in the bag, these 2 sentences becomes the same. The representation for these 2 will be exactly the same. And if we had 2 sentences like this in our training set, it will be only half as bad, because we'll produce, I would say, undefined results for this kind of sentences. But if we had first one in training and then the second one in our production, then we would conclude that, well, it is definitely a positive review. So we have to watch for that. One of the ways of anticipating that is to use a sequence of one-hot vectors. So instead of smashing them all into the one, we just concatenate the sequence. And one word in practice, if you plan to do it that way, use sparse matrices from scikit-learn, for example, because sparse representations will be much more memory efficient here. And if we have another sentence, like a quick brown vixen, where vixen it's a female fox, it's not in our dictionary, we will need to assign the unknown tag to it. But since every single word will go into this unknown bag, it may be not so good for our performance. Instead of doing that, we can assign, for example, either the synset for that word. If it is a dictionary, we can try that. But we can also try assigning the specific parts of speech that this given word represent. And this actually improved my results, especially when I had a very small dictionary of 1,000 words. It boosted, I think, from 86 to 89%, so really good if you want to work with small dictionary. And I also played a little and created model only on the part of speeches. And I know it doesn't make sense, but it actually had better results than 50%. So it wasn't totally random. It had like 60, I think. So I think the outcome is that people, when are angry and do not like something, will write in different style than people that are happy with something. And this is example network. We have our input, two dense layers, and output. Simple enough. Another way to approaching, well, since the part of speeches for unknown tags worked, maybe we could assign them to every word. Maybe it will improve something. And then we will have even bigger dictionary because we'll also want to include the part of speeches there. But for me, it didn't help anything. But remember, that was only my case on this IMDb. For you, it may improve something. Another way of representing these features, like first we had this sparse representation of matrices, and here we can have a dense representation. So to each word, we assign much smaller vector, but not only one hot values, but whole range from -1 to 1 usually, and also usually this vector will have length of 1, because then we have calculate this cosine similarity easier and better. And here I also created with the embeddings for the words and then with the parts of speech another model. Why 5060 input? Because we have 5,000 words and about 60 possible part of speeches from the spacing. And then by 1,000 because it was how big my review can be. Also, the problem is that I had to pad those sequences to work with those network. Pad, so either extend it by this token pad or cut them if they were too long. So we lose some information. Pros and cons of fully connected networks with sequence. It's still simple, so cheap and fast to learn, still under 2 seconds. Order of words matter now. They are still kind of interpretable, but we can't get close to state of the art, 0.96, and words at given position matter more. What do I mean by that? Because of how neural network works, if the word bad occurred here at the first position and then it occurred at the second or third, it will be treated not completely, but it will be treated differently. And that also may be a problem. And negations are, thanks to that, hard to catch. Not impossible, but hard. If you want to learn more about BASIC, I think that Andrew NG deep learning course is the best way to start. So you have a link. If we have a review, this movie was not good, and we have a negation, like I mentioned, it's hard to catch, we can use a few things to anticipate that. We can use a tool called word2phrase. It's from word2vec repository. And we can also use similar to in GenSim, but the upside of the one from the word2vec, it's written in C and it's blazing fast. On the few million sentences dataset, it works in seconds. In GenSim, I wasn't patient enough to wait for the result. And word2phrase or GenSim will produce these sentences. So now we have another word in our dictionary. Instead of having not and good separately, we will have them together. It works by looking how often these words occur together and how often they are separated. Simplifying. Okay, but the other way of anticipating that issue is, for example, to use convolutional neural networks, CNNs. I know that they are used usually on the images, and today I learned that can be also used on audio transcriptions or on audio in general, but we can also apply them to text. Let's think about this review. This movie was not good. What CNNs will do, will have this sliding window of one, let's say, neuron that will first conclude the representation of the words inside that window. So for this example, I choose the window of 2 words. We will have this matrix that will multiply our representation of this and movie, and we will create the representation of this movie together. Then for the movie was, I will have representation for those 2 words. And so on and so on, and we have everything. And this part of the operation is called convolution. And then we do operation called pooling. So we reduce dimensionality. And pooling does not go in sliding window. It goes over the multiple representations and reduce dimensionality. I think that's better to show. Basically, then we have a final representation of the triplets of words. And on top of that, we will use standard fully connected network. You can use either max pooling, so in each dimension we will pick one maximum value, or average pooling. So in each dimension we will calculate the average of the value in vector. I've heard that for text it's usually better to use max pooling, but I think it's always best to try both and find out what works for you. It's just another hyperparameter. For the convolution, you have the window size, how big it is, and also the stride size. So how many words you will jump. If here the stride size was 1 and the window size was also 2, so we move our window size 2 every 1 word. If we had the stride of size 2, then we would only have representations for this movie, then was not. And it may work with bigger strides, especially when you have long texts. So if you want to work on whole paragraphs, please consider that. And that's the simple architecture, and that's another architecture I came up with. Pros and cons of CNNs, they parallelize nicely and have much fewer parameters than the fully connected neural networks. Usually, of course, it depends how you build stuff. Order of words matter, finally. Position of words also matter. And if we want, we can create a network that will look at the whole sentence. It's not so easy in practice, but in theory we can. And if you want to learn more about the stuff, another further reading, Understanding Convolutional Neural Networks for NLP, I also recommend reading that. So now recurrent neural networks. Remember how in CNNs we had a representation constructed of the 2 words together. Now we will have a representation for the word this. Then we move to the next word. We create a representation for the word movie, but we also take the previous word into the context. Then we create a representation for the word was, but we also take into account the previous words. And we always use the same matrix of weights. And when we get to the end, we'll have a representation of the whole sentence. And this is really, really nice because in theory, we catch the whole sentence, we know what is there, and we can work on that. But the problem here is we usually we can have problems with vanishing gradients. And I will talk about that in a second. And fully connected on top, and now we can create a prediction. We can also stack those layers like a regular network. And when we have a review like terrible, I loved her previous movies, the word terrible that indicates sentiment is at the beginning. And when we get to the end, our representation will have to go through very deep network and we'll have to deal with problems like a vanishing gradient, when it will totally vanish and we will lose the meaning of the word terrible, or exploding, because we are always multiplying by the same matrices of weights. To anticipate that, we can use bidirectional RNNs. So first we'll go front to back, then back to front, merge in some way the results, either concatenate some whatever, and fully connected network on top. It should work. So pros and cons can give better results. We look at the whole sentence, but they are hard to train because, as you may see, the network will be as big as your sentence is, or whole review. So we will have to deal with training very deep networks, and this is really, really slow. If you want to learn more about RNNs, I put a link to the Stanford lecture about it. So what is another way to anticipate that forgetting? We can use LSTMs or GRUs. And unfortunately, I won't get into the detail here because, well, the architecture of the neurons is really complex. This is LSTM. We pass the state, and we not only pass the representation, but we also pass the, let's say, state of the cell. And these are GRUs. These are a little simpler, but the important thing is we do not only carry then representation for what happened in the past in the vector, but we also will carry a state. And since it's more complex and we have more operation and gates that remember or forget things, we won't be necessarily forgetting stuff. So since it's not always the simple matrix multiplication like it was in RNNs, we will contain the info about the words at the beginning. But again, as you may see, the design is pretty complex. So when we are training network, we have to do a lot of operations, a lot of backpropagation, so it will take time. But they can give best results, and until the transformer came up, they were most of the time state-of-the-art. And we can create, even in Keras, the architecture that will look at the whole sentences. It's hard, but it's possible. And here another lecture from Stanford and link to a blog post about understanding LSTM networks. Now, going back to the result of my experiments, they weren't really successful. So fully connected network with a bag of words achieved 0.89 accuracy, while LSTM were really near. It was 88%, but the training time was like 60 times higher. So it's not always worth it to throw yourself into the most complex architecture at the beginning. I think that it's always best to start with something simple and then iterate and compare with that. Because with the simple architectures, you will also gain the quick inference time, which can be really useful. And if you are, I barely scratched the surface here, and if you are interested in the machine learning in context of NLP, I highly recommend that book. It's, I think, not only the one to read, but also the one, if you want to work in that, to have, because I find myself often going back to reading specific parts, because, for example, if you know how the size of the window in work2vec works with the produced embeddings, you can find it there. So that will be all, and thank you.